All right, so like Stuart mentioned, my name is John, and today I'm going to be talking about Federated Learning for Health, which is a project that I've been working on at Vector Institute. And I want to first off acknowledge a lot of my colleagues, both at Vector and elsewhere, who have been a big part of this work. And what I'm going to be discussing today is leveraging federated learning to train performant machine learning models in the healthcare context. So the motivation of this work is a vision of the future where machine learning models can transform the healthcare industry by augmenting existing diagnostic and treatment workflows to enhance efficiency and robustness. But one of the major challenges is that machine learning models often require large amounts of data, and in the healthcare industry, data is siloed with high barriers to access. So the implication here is if we can't harness the collective data, we won't be able to train performant machine learning models and deploy them in the healthcare sector. So one of the potential solutions to this data problem is to leverage federated learning, which enables us to jointly train machine learning models on data that is not co-located, effectively allowing us to increase the data set size without having to explicitly share data across organizational boundaries. And when we discuss federated learning, there's often two types that are discussed. One is horizontal federated learning, where we have two or more organizations, which we're going to call clients, and they have the same feature space in the same label space, and they want to collaborate to jointly train a machine learning model that maps their inputs to outputs. In the case of vertical federated learning, again, we have multiple organizations, which we refer to as clients, but each of these clients is going to have features about a particular sample. So for an example, we can be trying to make a prediction about a certain patient at a hospital, and some of their medical records might be at one institution and other medical records at another institution. So in vertical federated learning, we're trying to do federated learning and increase the feature dimension when we're inferring about a particular sample. And some of the promises of federated learning are increased model performance. So by virtue of leveraging a larger data set, we can get better performance. And we're also leveraging data from multiple sources, different hospitals. So by having more diverse data set, we can be more robust to different patient populations. Federated learning also affords us some privacy. So by keeping data local on clients, we're reducing the chance of private data exposure. I do want to mention, though, that federated learning is not the be-all and end-all, and there's other privacy-enhancing technologies that we have to layer in on top if we're looking to do deployments. And then lastly, a nice benefit is just by virtue of how federated learning is designed, we can kind of retrain the model at set intervals as data is added at different hospital sites. So I just want to quickly touch on a few use cases of federated learning in the context of healthcare. There's been a ton recently, so if you just search the internet, you can find some. But these two were particularly interesting. The one on the left panel is actually the largest FL study to date in terms of the amount of healthcare institutions that were involved. There was 71 sites across 6 continents. And they collaborated to train a tumor boundary detector for a rare disease, and they're able to outperform a non-federated learning approach by a significant margin. And we also saw NVIDIA do a lot of work in this space, and just highlighting one of their recent examples of using federated learning is a collaboration that they led with 20 hospitals across 5 continents. And here they were focusing on COVID classification tasks with tabular features. And again, we're able to train a very performant model better than siloed training. So just to narrow the scope of the discussion today, I'm going to be focusing on horizontal federated learning. So that's the setting that I spoke of earlier, where each of one of the clients or hospitals is going to have the same type of data set with the same features and the same labels. And cross-silo is an assumption about how large of a client pool we're going to have. So how many organizations are going to be participating. And in cross-silo, we assume a small client pool with moderate to large compute and data sets. And when we talk about horizontal cross-silo federated learning, at a high level, it kind of looks like this diagram. We're going to have a server as well as a number of clients, which are the healthcare organizations. And the server is going to start by randomly initializing a model with random weights, distributing this model to each of the hospitals who are going to train on their local data. And the hospitals are going to upload the updated weights to the server, which reaggregates the weights and distributes them in the next round. And when we talk about federated learning, we're basically just trying to minimize the average expected loss across clients. So each client is going to have a loss function, let's call it F. That's a function of their local client data xi and w, the model weights. And we're basically trying to find the weights that minimize the average expected loss. And there's a few different ways that we can approach this objective. Two of the seminal ones are FedSGD and federated averaging. In FedSGD, we're simply going to distribute the weights from the server to all of the clients. The clients are going to sample a batch of data and perform a forward and backward pass, and then communicate back the average gradient to the server, which is going to average it across all of the client gradients to get a pseudo gradient that they use to update the global parameters. And the nice thing about FedSGD is it's actually equivalent to centralized large batch training, but it actually requires per batch synchronization with the server, so it's often not feasible to use in practice, especially in cases where we have large numbers of clients, lots of training steps, and other factors. So federated averaging was proposed, and it's going to incur a lower communication cost by trading off some convergence potentially. And how federated averaging works, it's very similar. Instead of assuming that all of our clients are going to be participating in every round, which is a strong assumption, we're going to sample M of N clients. And each of those clients is, again, going to get a copy of the weights from the server. But instead of just taking one optimization step locally, we're going to take a specified number of steps locally and then transmit the weights back. So by virtue of not sampling all of the clients and by taking more than one optimization step locally, we're going to have to communicate with the server less. But the trade-off here is it's actually not equivalent to centralized training, which may affect our convergence. In terms of some of the challenges that we face in federated learning, one of them is heterogeneous data. So we're working with different hospitals with different patient populations and different equipment. There's heterogeneous systems. So when we're doing federated learning, some hospitals may have lots of GPUs and lots of compute, whereas other hospitals may have relatively less. So it kind of can constrain the types of architectures we can train. There's data privacy. So like I mentioned before, federated learning is going to give us a basic level of privacy with the data locality, but we still have to have other considerations. And then lastly, communication. Like I mentioned, communication is a bottleneck in federated learning. So just to dive into one of these challenges really quickly. So what do I even mean about heterogeneous data? And all I mean is that there's distribution shifts between the clients. So the joint distribution of inputs and targets varies between the data sets. And this is something that we actually see in the standard ML setup, but it's usually between the train set and the test set. So the same thing can occur, but between client data sets. But it's all of the distribution shifts that we're kind of familiar with from classic machine learning, like label shifts, where we have different label distributions on different clients, and covariate shift, where we have different distributed input data on each of the clients. So a recent use case that I was working on that kind of exhibited some covariate shift is this kidney histopathology use case. So kidney histopathology is a branch of pathology where we're basically examining cross-sections of kidney tissue under a microscope and looking at these digitized slides. And due to variation in the scanning equipment and the materials used to stain the tissue at different hospitals, you can see that the images look slightly different between hospital sites. So why does heterogeneous data matter? It actually matters because it changes the optimization landscape. So if you take a look at the right panel, which is a really simplified convex setting where we're looking at the surface of the loss functions. F1 and F2 are the client loss functions, and then we have the combined loss function, F1 plus F2 divided by 2. And you could see that the optimum of the client loss functions and the global loss functions are actually distinct. And federated SGD will converge to the global optimum in this convex setting, but federated averaging will not. And that's because of the thing I discussed previously. We're taking more than one training step locally, so the parameters begin to drift from their trajectory towards the optimal point. And this effect gets worse as data begins to have larger distribution shifts. So there's a bunch of ways in the literature to effectively address heterogeneous data. I'll just mention a few quickly. There's local fine-tuning, where we can fine-tune our model on a local data distribution. There's contextualization, where we can leverage features at different client sites to inform personalization or make better predictions for a given client. There's model interpolation, where we have a global model trained through federated learning and also local models that are trained locally, and we try to find some optimal combination of either the weights of these models or the predictions of these models, and there's many more approaches. But I'm going to change gears and talk a bit about Federated Learning for Health, which is an open source library that makes it easy to work with state-of-the-art federated learning methods. And our vision for this package is really to make it easy for hospitals to collaborate to train performant machine learning models that are more performant than they would be able to if they just considered their own data set, and even in some cases better than if they pool all their data together, which I'll get into later. So there's a lot of different components a part of Federated Learning for Health. So if you're actually interested in it, I'd encourage you to go to the GitHub, which I'll show later, but I'll just highlight some of the components. So we have like tons of different optimization strategies, all the way from seminal federated learning algorithms to really cutting edge ones. A lot of utilities to work with data in a distributed manner. So federated feature processing like feature alignment, federated dimensionality reduction, and federated synthetic data generation. We also have layered in or incorporated other privacy enhancing techniques like secure aggregation and differential privacy, and tons of other things that I won't go into. But one of the things we've been working on recently, and I mean like very recently, is this thing called Florist, which is a user-friendly web interface that enables easily interacting with the federated learning workflow. And we want this to be leveraged by developers and researchers, but also domain experts from the healthcare sector to get them integrated into this workflow. And it's probably no surprise that the users that we're targeting are in the healthcare domain. So we've been working a lot recently with researchers, really trying to solve some pain points in designing and conducting federated learning experiments, identifying suitable FL methods that they'd be interested in incorporating as baselines, and supporting them in easily being able to create new federated learning methods. We also want to start collaborating more with developers at different organizations who are looking to build custom FL applications for their organization's needs. And eventually, we really hope to also collaborate a lot with domain experts and build out functionality that's helpful for them. I don't have like a lot of time to go through the code, so I won't spend too much time on this slide, but I just really want to drive home how easy it is to spin up a federated learning experiment with our framework. So all you have to do is define code for the server and code for the client, which are the two main components in federated learning. So on the left, we have the server code, and if you take a look in the main function, all we are doing essentially is we're first setting some configuration parameters. Then we define the federated learning strategy, which is going to dictate when we get the parameters from the clients, how are we going to aggregate these parameters and to yield a new set of parameters that's going to be distributed to the clients in the next round. In this case, we're doing federated averaging, but we have a bunch of other strategies, some of which are much more complicated. And then after we define the strategy, which basically governs how we aggregate the parameters, we can define the server. And the server is going to take in the strategy that we just defined, as well as a client manager. And the client manager dictates how we sample clients for every federated learning round. And then after that, we can just pass in some initialization arguments and start the server. And then if we hop over to the client code, all we have to do on the client side is basically define how the client is going to get their data, so get their data loaders, define what optimizer they're going to be using, what model they're going to be training, and the local loss function. And we could also pass some metrics that we want to calculate on the local data, and then we can simply start the client. And we'll run this client code for each one of the clients that we have, and once we start the server and start the client code, federated learning will kick off automatically. So changing gears to talk about some clinical benchmarking results that we obtain with federated learning for health. This first set of benchmarks is called FLAMBI, and it's data sets sourced from real hospitals from a variety of different tasks. So we have 3D segmentation tasks from MRI scans. We have this multi-class classification task, and then we also have this tabular prediction or binary classification task. And you can see on the right side, I've just visualized, some of at the top there. That's the intensity distribution of the scans across the different hospitals for FedIXI, and you can see there's quite a bit of variation in the distribution of the data across the different hospitals, and you can see again with the other figure there. So these are the results, and I know there's a lot here, so I'm gonna walk you through it so it makes sense. Across the top, we have the 3 data sets, so Fed Heart Disease, FedIXI, and FedISIC. And then we have 2 panels. And the top panel is going to be the federated learning methods. And in the bottom panel is going to be our baselines. So I'll start by explaining our baselines. The first baseline that we see is silo. So this is the setting where each hospital only considers their own local data. So they're going to train on their local train set and then evaluate on their test set. And then we're going to average the performance across the test set to get the metric that you see there. There's also central. So central is a stronger baseline where hospitals decide to collaborate by pooling all of their data together, and we train a model on the pooled data and test on the pooled test set. And then we have the client-specific baselines, which are if we train a model on this client's data and then we distribute it to the other clients to evaluate on their test set and average the performance, that's how those baselines are calculated. So those are the baselines. I'll move up to the federated learning methods. And you can see for each data set, we have 2 columns, global and local. This is just going to be the checkpointing strategy that we use. So since we're doing federated learning, we have some choices about how we want to checkpoint. Do we want to checkpoint based on the average, the lowest average loss across clients? Or do we want to do local checkpointing where for each client, we're going to save the checkpoint that works best for their specific data? So that's the distinction between global and local. And you'll see that 5 of the federated learning methods only have local results, and these 5 methods are personalized federated learning methods, which at the end of the federated learning procedure, each client is going to have their own personal model. So it doesn't really make sense for them to have, you can't do global checkpointing. They're only going to have personalized models, so we can only do local checkpointing. And for this first set of benchmarks on these 3 data sets, we can see that federated learning outperforms all of the baselines. This includes siloed evaluation, where each hospital is only considering their own data set, but also the setting where all of the hospitals are pooling their data together and training a model. And I think this is really impressive. And the reason is, for these personalized federated learning methods, each of them is going to have parameters or have a custom model that's suited for a specific site. So it's actually able to outperform this centralized baseline, which is really, really, really cool. So the next data set we're going to go over is a Gemini data set. So this is actually sourced from Canadian hospitals from 2015 to 2020, and there's 7 hospitals in total. And we're basically trying to predict whether or not a patient's visit will end in mortality. And again, this is a real healthcare data set, so we see some pretty heavy distribution shifts in it. And if we look at the results, which are laid out in the exact same way, we could see again, federated learning methods are outperforming all of our baselines. And in particular, the personalized federated learning methods are performing the strongest. And then lastly, I'm going to talk about this delirium development data set, which is also from the Gemini consortium. And it's basically a classification task to see if delirium has occurred within a patient's stay. And again, we have lots of distribution shifts as a real-world data set. And going into the results, we can see, again, federated learning methods are performing the best. In this case, we have FedProx that is a non-personalized method, actually get the best results in terms of mean accuracy, but FendaFL gets the best results in terms of AUC, and this is often a metric we care about more. And yeah, it's a personalized federated learning method that outperforms all of our baselines. So that's kind of all of the content I have planned to go over today. I just want to quickly mention some of the collaborations that we've been working on. I mentioned quickly like working with the Gemini consortium and trying to see if federated learning could be used for prediction tasks like mortality prediction and delirium prediction. We have more research-focused kind of endeavors where we're looking at developing new methods for differential privacy within the context of federated learning. And lastly, the collaboration that I'm personally most excited about is one with Mount Sinai, particularly the Hader Lab. And we're working with kind of prostate MRIs and trying to do clinically significant prostate cancer detection. So a lot of collaborations, and we're always open to new collaboration and contributions. So that brings me to the end of my talk. Thanks so much for coming. I know there's like a lot of other great talks at the same time, so it means a lot that you guys came and watched mine. If you're interested in federated learning or federated learning for health, feel free to check out our GitHub, leave us a star, and yeah, feel free to reach out if you have any questions about the talk.
Thanks so much. We probably have time for maybe one quick question. Go.
What makes this for health? Let's just say I wanted to do something similar. So the question is, what makes this for health? Let's just say I wanted to do something with a different domain, like cybersecurity. Could I use the same package?
Yeah, I think, but honestly, a lot of the features that we support now are like just like general federated learning methods, so you can definitely use this package. I think just we catered a lot of the utilities to like loading, healthcare data and things like that, but there's definitely, it's built in a general enough way, like the code I went over, like you can just like really have full flexibility on what data you train on, so you can definitely use it in that context. And it's definitely something we're interested in as we like scale this project up. If there's other industries like cybersecurity or finance that this makes sense in, we definitely want to kind of support those use cases.
Thank you.
Great. Thank you so much, everyone.